Centripetal force is a force that makes an object that would otherwise go straight turn in a circle. If you've ever been on a merry-go-round, then you've likely experienced centripetal force. As the merry-go-round spins around, your body likely feels a sensation of being thrust outward, away from the center of the circle. At the same time, you use your arms to pull you inward so you keep turning in a circle. That's centripetal force. You'll recall that the faster the merry-go-round spun, the harder it was to hang on and keep going in a circle. That's because the equation for centripetal force is your mass times the velocity you're spinning squared divided by the radius of the circle. In other words, the faster you spin, the more centripetal force is needed to keep you going in a circle. The term centripetal force is actually a bit of a misnomer, because there really is no centripetal force out there in the universe causing things to turn. Instead, the centripetal force equation is a measurement of how much other force you would need to make an object turn. In the case of a car turning on a road, the centripetal force is provided by the friction. So to find out how much force you would need to make a car turn, you could use the frictional force equation. That is, if you want a car to turn in a circle, the mass of the car times the gravity times the frictional coefficient must be greater than or equal to the mass of the car times its velocity squared divided by the radius you're turning. You can see the faster the car drives, the more frictional force you're going to need. In the case of tetherball, the centripetal force is provided by the tension in the rope. In the case of a roller coaster, the centripetal force is provided by the normal force of the steel beams. In the case of an orbit, the gravitational force is perfectly equal to the centripetal force. In other words, the gravitational constant times the mass of the big object times the mass of the little object divided by the radius squared is equal to the mass of the orbiting object times its velocity squared divided by the radius. In order to maintain an orbit, this equation has to be balanced. The gravitational force has to equal the centripetal force, otherwise you don't have an orbit. In the case of the Earth and the Moon, if the gravitational force was too strong, the Moon would come crashing into the Earth. If, on the other hand, the gravitational force was not strong enough, the Moon would spin and then fly off into space. The internet is full of examples of people spinning on a merry-go-round where the centripetal force required to keep them going in a circle simply exceeded the force pulling them in. So, they flew off the merry-go-round. So here's a fairly standard centripetal force equation. We have a car driving down a road. The force that's making the car turn is friction. So we simply set our equation for the force of friction to be equal to the centripetal force, or our mass times the gravity times the frictional coefficient of the car has to be greater than or equal to the mass of the car times its velocity squared divided by the radius of the turn. In this case, we don't know the mass of the car, but we can still use the equation. So, mass times a gravity of 10 times a frictional coefficient of 0.20 must be greater than or equal to the mass of the car times the velocity squared divided by a radius of 50. Next, we simplify the equation. 2m must be greater than or equal to mv squared divided by 50. Multiply everything by 50, and we get 100 times the mass is greater than or equal to the mass of the car times velocity squared. The m's cancel out, square root both sides, and we get the velocity must be less than or equal to 10 or 10 meters per second. Here's a problem that's a bit more complicated. It's going to have a lot of moving parts, but still centripetal force is going to play a major role. We have a child on a swing with a rope that's 5 meters long. The swing swings back and forth in a pendulum-like motion. Since the swing is turning in a circular motion, we know we're going to be using the centripetal force equation, which is mv squared divided by r. The equation gives us a lot of information. We know the radius. That's going to be the length of the rope, or 5 meters. We also know the mass of the child. That's going to be 50 kilograms. We don't know the velocity, so we have to get a bit creative on how we figure that out. we could modify our drawing a bit to create a right triangle like this. This is going to be helpful because they give us the angle of 60 degrees, which means our triangle is actually the 30-60-90 triangle. That's helpful because we've memorized the ratio of the sides for our 30-60-90 triangle, and that is the short side is x, the long side is 2x, and the medium side is x root 3. In this case, our 2x side is still the length of the rope, or 5 meters. So if 2x is equal to 5, then x must be equal to 2.5, which means this green side of the triangle is exactly half the length of the overall rope. Then, from our drawing, we can see that if this yellow piece of rope is 2.5 meters long, that means the swing is also 2.5 meters above its lowest point, or when it swings, it's going to fall 2.5 meters in the vertical direction. Now that we know the height of our swing is 2.5 meters, we can use some of the standard motion equations to calculate the velocity. The simplest one is going to be the velocity of a falling object is equal to the square root of 2 times the force of gravity times the height of the object. Or in this case, the velocity is equal to the square root of 2 times the force of gravity times a height of 2.5. Or velocity is equal to the square root of 50. You probably don't know the square root of 50, but in this case it's not going to matter because once we plug it back into this centripetal force equation, we end up squaring our velocity, which cancels out the radical. So our centripetal force is mv squared divided by r, or in this case, a mass of 50 times a velocity of the square root of 50 parentheses squared divided by a radius of 5 meters, or 50 times 50 divided by 5, which is equal to 500 or 500 newtons. Now to answer the question. In this case, they simply don't want to know the centripetal force. They want to know the total force on the swing, which means in addition to the centripetal force, we also have to add the standard force of gravity. Mass times gravity, pulling everything down all the time. Again, our mass is 50, our gravity is 10, so our total force from gravity is 500 newtons. So in the end, we have 500 newtons of force from gravity and 500 newtons from the circular motion of the swing, giving us a grand total of 1,000 newtons. In other words, at the bottom of the swing, the child appears to weigh twice as much as it would without the motion of the swing.